All right, let's continue in chapter 3 and look at going from grams to moles and then moles along to atoms. All right, so in order to go and convert in between grams and to moles to atoms, we need to remember a few things. One, molar mass always has units of grams per mole, and we know that Avogadro's number always has units of something per mole, and that something could be moles or atoms or whatever, or molecules or atoms or whatever, and we know this is 6.022 of whatever that manages to be, 23rd per mole. So if we want to go from moles into grams, we are simply going to multiply by the molar mass. If we want to go from grams into moles, we are going to divide by the molar mass. So let's look at an example. We want to find out how many moles of potassium are in 125 grams. So we know if we want to go from grams into moles, we are going to have to divide by the molar mass. So we're going to look up the molar mass of potassium and discover that the molar mass of potassium here, our K, has a molar mass of 39.10 grams per mole. So how are we going to do the problem? 125 grams. If we divide this by 39.10 grams per mole, our grams are going to cancel, and we're going to get an answer of 3.217 mole of potassium. If we wanted to know how many atoms that was, we would take and we would go into and use Avogadro's number. All right, so let's look at this one. We want to go from moles here into grams. We know that if we want to go from moles into grams, we're going to multiply by the molar mass. So we're going to start out 0.025 mole of argon. We're going to go to the periodic table, and we're going to realize that we have 39.95 grams per mole. Our mole is going to cancel, and we're going to have an answer here of 0.999 grams of argon. We only have 2 sig figs, so let's just call this 1.0 grams of argon. This would be argon atoms because argon exists as an atom. So continuing, if we have 2.25 moles of silver, how many atoms is that? Now, instead of going from grams into moles, we're going into how many atoms. When we are asked how many atoms, we know immediately that that is an Avogadro's number question. And if we have moles and we want to go into atoms, we are going to multiply by Avogadro's number. If we have atoms and we want to go into moles, we're going to divide by Avogadro's number. So here, moles to atoms, we're going to start out at 2.25 mole of silver. We know that there's 1 or 6.022 times 10 to the 23rd atoms per mole. And that is going to give us an answer here of 1.35 times 10 to the 24 atoms. All right, so let's start this out. We have 1.1 times 10 to the 22nd atoms of barium. Now we know that there are 1 mole of anything, in this case barium, for every 6.022 times 10 to the 23rd barium atoms. You can take and either say we're going to divide by Avogadro's number or multiply by the inverse. It's the same thing. And this is going to give us 0.0183 mole of barium. Now we're looking for grams. In order to go from grams, we can't start directly in atoms. We have to go through moles. We can go to the periodic table and look up the molar mass of barium. We know to go from moles into grams, we have to multiply by the molar mass. The molar mass of barium is 137 grams per mole. Our moles cancel, and that is going to give us a total of 2.50 grams of barium atoms. All right, let's go straight through on this one. We want to know how many copper atoms are in 2.5 times 10 to the 4th grams of copper. So we're going to have to go from In order to do this, we have to go from grams to moles, and then we have to go from moles to the number of atoms. We know to go from grams to moles, we're going to divide by the molar mass. We know to go from moles to atoms, we're going to multiply by Avogadro's number. So all we need off of the periodic table is the molar mass of copper. So the molar mass of copper off the periodic table is 63.55 grams per mole. So let's get this started. 25.4 grams of copper. 1 mole divided by 63.55. Again, this is the same as dividing by 63.55. It's going to get you an answer in moles. And then we know that we're going to multiply through 6.022 times 10 to the 23rd atoms of copper per mole. Our grams of copper cancel, our moles of copper cancel, and we're going to get a total here of 2.41 times 10 to the 23rd atoms of copper. All right, same thing. Start out by the grams of aluminum. We know in order to get from grams into atoms, we're going to have to divide by the molar mass, multiply by Avogadro's number. Off the periodic table, the molar mass of aluminum is 26.98 grams for every mole. Our grams will cancel, and this is going to give us moles of aluminum. We know to go to atoms, we're going to multiply by Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. We're going to multiply through this, and we're going to get a value of 3.62 times 10 to the 23rd aluminum atoms in this aluminum can. All right, let's look at a molecule instead. It works exactly the same way. If I want to go from grams to moles, I'm going to take and I'm going to divide by molar mass. Now, the molar mass of glycine here is given as 75.07 grams per mole. So if we start out with 28.75 grams of glycine, we know there's 1 mole for every 75.07 grams of glycine, and that is going to give us a total here of 0.3830 mole of the compound of our glycine. Now, let's ask a different question. Instead of just going for moles of the compound, let's consider moles of the individual atoms within the compound. And let's realize that if we have 1 mole of this total glycine, we're going to have 2 moles of carbon, we're going to have 5 moles of hydrogen, etc. So if we wanted to ask on a secondary question here, how many moles of hydrogen are in our 28.75 grams of this compound, we're going to have to realize that we're going to have to take moles of glycine and multiply by the ratio of atoms of hydrogen for every molecule of this stuff, or moles if you want to look at it that way. So let's start out 0.3830 mole of glycine. We know that from the formula, we have 5 moles of hydrogen, and we're solving for hydrogen here. And remember, this is moles of the element for every 1 mole of our glycine. And this is going to give us a total of 1.915 mole of hydrogen. And we can do this for any element. For example, nitrogen would be 1 to 1. Oxygen would be twice as many oxygens, or 2 moles of oxygen for every 1 mole of the compound, etc. All right, let's continue and let's look at our molar masses and our grams. We want to know how many grams of this vitamin C is in this number of moles. The rest of this information is completely irrelevant to the question. We're starting out at 1.42 times 10 to the minus 4 moles of our vitamin C. And we're asking how many grams that is. Well, the molar mass of vitamin C is 176 grams per mole. We only have 3 sig figs in our question, so we only need 3 sig figs here. And that is going to give us a total here of 0.0250 grams of vitamin C in the daily allowance for vitamin C for children aged 4 through 8. All right, let's consider the last question. We have a container of artificial sweetener that contains saccharin. Saccharin has this formula right here. It's given as this ratio above, and you can calculate it, but the molar mass here is given as 183.18 grams per mole. And the question is, how many saccharin molecules, so we're asking how many molecules, so we know that this is an Avogadro's number calculation, are in this sample, and then we want to know how many carbon atoms are in this sample. So let's realize that we have 7 carbons for every 1 saccharin. Okay, we're going to need that in a moment. We have the molar mass, so we're going to go from grams to moles, moles to molecules using Avogadro's number, and then we're going to use our ratio of 7 to 1 to get atoms of carbon. So again, making sure that written down you have someplace that we have 40 milligrams and we have 183.18 grams per mole. So we have 183. Now note that's 3 sig figs, so I'm going to stop the molar mass at 3 sig figs. That's grams per mole of the saccharin. We know that Avogadro's number is 6.022 times 10 to the 23rd per mole of anything, and we know there's 7 carbons for every 1 saccharin. With all of this in mind, 40 milligrams. Make sure we remember our metric prefixes. We know that a milligram is 1,000, or that there is a gram for every 1,000 milligrams. This is going to give us grams of saccharin. We know there's 1 mole of saccharin for every 183 grams of saccharin. And this is going to give us moles. Now I'm going to stop the math here just to make it maybe a little bit clearer. And this is going to be 0.000218. And I've got an extra sig fig here, mole of saccharin. I'm looking for molecules. Well, to go from moles to molecules, I need Avogadro's number, so 0.000218 mole. We know that there are 6.022 times 10 to the 23rd molecules per mole for our saccharin, and this is going to give us a total of 1.315 times 10 to the 20th saccharin molecules. The last thing we were going to solve for was atoms of carbon. Now, to get atoms of carbon, we need to do our last piece of information, and that is going to be 7 to 1. We know there's 7 carbon atoms for every 1 saccharin. And if we finish up our math on this one, we're going to get a total, changing colors here to make it a little more obvious, of 9.205 times 10 to the 20th carbon atoms.